I think we can start. Today, we are going to see a completely different tutorial. We are going to discuss how to reduce data from imaging atmospheric Cherenkov telescopes. Okay. There is a huge problem with this kind of analysis for a school if we compare with Fermi, because Fermi has public data. Here we don't have public data. Actually, we have one run, which is equivalent to 10 minutes of observations, which is free for everybody. And I took this run and I copied 3 more times and shaked the data, and then I simulated new data so we can play. Okay. So this data is already in these computers from 1 to 29. And I'll give you some brief introduction to Cherenkov telescopes. I know that Michele Doro already gave a talk about that, so I'll be quick. But before starting effectively the lesson, I want to tell you some quick things about yesterday's lesson on Easy Fermi. This is the GitHub of Easy Fermi. If you use Easy Fermi for your research, please give me a star here. It helps a lot with the divulgation of the software. If you have doubts on how to use Easy Fermi, you can check the YouTube tutorials, or you can chat with me, or you can write me, okay? So feel free to contact me if you have any problem. We also have a very complete documentation for Easy Fermi. So it's not only the YouTube tutorials. You can find the documentation here on GitHub if you click in this link. So it's very complete. The detail, everything that's going on behind the scenes, okay? So that's it about Easy Fermi. And for those of you that yesterday could not do the spectrum or the light curve, if you want, we can meet during lunchtime or after the lesson of today, which will be quite short, and we can discuss one-on-one or in small groups how to do the analysis, okay? Okay, let's start with the Cherenkov analysis. I will ask you to go to the Documentos. It's a folder called Documentos, computers 1 to 29. And then you can open the folder LST 2025-08, I think. Okay, open the terminal in this folder too. Open the terminal. Okay. With the terminal open, you do Mamba activate by SWGO. This is the software for the instrument that we are going to work tomorrow. However, this software comes with Gamma Pi, which is the only thing we need to do this Cherenkov analysis. Okay? Once you do that, you do Jupyter Notebook, press enter. I already opened it, okay? In my case, it's here. Did you manage to open Jupyter Notebook? Hmm? Yes, of course. Mamba, okay. If you can read, is Mamba activate by SWGO, and then Jupyter Notebook with Y. Jupyter Notebook. Okay, just press enter. And then you can open, you see something like that, and you can open this tutorial, the ICTP-2 EACT stereo analysis. Did you all manage to do that? Okay, you all open the notebook. Perfect. Okay, everybody. So for doing Cherenkov observations are very, very tricky to do, because especially because the signal is tiny. is very, very small compared to the noise. A very strong source in the sky is the Crab Nebula. To give you some notion about this noise that I'm speaking about. For the Crab Nebula, which is one of the strongest sources in the sky in gamma rays, we have about 1 gamma ray photon for every 1,000 gamma ray, for every 1,000 cosmic rays coming from the same direction. Okay, so we have to filter a lot. This is for the Crab Nebula. For a normal blazar, we have 1 photon every 1 million events. So you can imagine how good you have to be in selecting, in identifying the cascades and telling them apart. It's better if we use several telescopes for doing that, but we can do also with monoscopic observations. Here is a schematics of how magic telescopes work. So we have the 2 telescopes here. We have a cascade, and every telescope, each telescope, we observe the cascade in a different orientation. We fit an ellipse. We call this the Hillas ellipse. In each one of these cascades, actually is the same cascade observed from different angles, and then we can reconstruct the position of the source. Okay. It's much harder than it sounds. And after fitting the ellipse, we have a bunch of parameters. Skew of the ellipse, semi-major axis, the semi-minor axis, a lot of parameters that we feed into a random forest. And the random forest will tell, okay, this is a cosmic ray, this is a gamma ray. There is an extra problem, which are electron cosmic rays. Electron cosmic rays generate cascades that are identical to gamma ray cascades. So this is an unsubtractable background. Okay, so we have more problems than you can imagine here. Well, okay, we can start. I will work with you with data level 3, which is the final data level. This will be the data level available for the users once the telescope is working, the CTA is working, okay? If you enter in CTA now, you have to work with DL0, DL1, and DL2 data. And this is much time consuming, and it's not worth to do this in high school, okay? But if you are curious, you can access these 2 links here and take a look by yourselves. This will be here. But this will basically apply the random forests, actually fit the ellipses, apply the random forests, select what is photon, what is cosmic ray, and finally apply the instrument response function to recover the reduced data. Okay. Okay, we can start. This is the difference, for instance, of a gamma ray shower compared to a cosmic ray shower. We can start by importing some Python libraries. The most important one will be GammaPy, okay? And we have to load the gamma ray data. This is a very straightforward tutorial to follow. So load the gamma ray data. We have 4 runs. I told you that originally we had only 1, but then I kind of simulated the other 3 based on this first. For you that took the data with me, please just correct the path on your computer. Marcela, you raise your hand. No, warning is not a problem. Yeah. Okay, so we can select all the runs that we have. Or the real run here is only 1, but we are using 3 fake runs. And here is just a clever but not so clever way to selecting the number of these runs in the string. So we just need these numbers here because these numbers are inside the metadata. Yes? What? Zoom in. Let me try. better. Okay. So we just selected the runs. Oh, I was right in the middle. Okay. And okay, once we select the runs, let's take a look on the metadata of these observations. Okay, they are very similar because they are basically the same that I just shuffled by hand. Okay. Now we can take the target position. This is the Crab Nebula. So these are the coordinates of the Crab Nebula. And now we can start the data reduction chain. However, first I want to discuss something very particular about gamma ray astronomy. In the past, in the beginning of the magic era, the telescopes were pointed to the source. This may sound obvious, but nowadays we don't do that anymore. Because to estimate the background, the astronomers pointed to the source. And then, let's say 3 hours of observations. Gamma rays is like that, not like optical. You have to wait for much longer times. Then, okay, you observe that source for 3 hours. Then you point your telescope to another region of the sky where you expect that the background is similar to the region that you are observing, and observe for extra 3 hours so that you can remove this background from your target. This was the standard technique in the beginning of the magic era. Okay, nowadays we do differently. So imagine your source is the yellow star over there. We point the telescope here. Like typically we use a distance of 0.4 degree because the sensitivity in the camera is not homogeneous. Okay? In the center is much more sensitive than in the borders. So we point to a region like here, which is 0.4 degrees from our target. The exposure time will have to be a bit longer, not that much. Let's say originally it was 3, now it will be 3.5. And we use this region here as the background. So we are using, or we can use more backgrounds as we will do in the tutorial. So we do this wobble technique that we observe here, then we move the telescope over there, and we have these regions in opposite directions or here, that from which we can estimate the background, okay? Because in this ring here, the sensitivity of the camera is the same, okay? Okay, you see the wobble points in the analysis very soon. Okay, okay, here we have to define the limits for the data. In this case, we are using 100 GeV up to 1 TeV, and in this other block here, we are defining what they call in Cherenkov astronomy the real axis. I don't like this name because this is the fake axis, but they call it the real axis. This is the axis at which we are plotting, just that. While this block above is the axis of the data. So you cannot go below 100 here because you can get convergence problems in your field. Okay. So let's go ahead here. See, I'm sorry. Here I'm defining the number of off regions, which are this here. This is an off region. I'm defining 3 because I'm taking this, and this. Okay? So I define the number of off regions. Now, now we have to define something that is not very intuitive, is the region geometry, which has everything to do with the number of pixels and the size of the camera. Okay, we create these empty objects. You can see this kind of function here, the spectrum data set maker. We are creating a lot of empty objects here. If you don't know what's a spectrum dataset maker and you go to Gamma Pi documentation, you find that is the maker that does the dataset spectrum. Yes, it's not, so it's not very helpful. Okay, so continue with creating these empty objects. Let's create a counts map. Oh. And here you see a very ugly counts map because it's empty. Okay, but we'll solve this problem soon. Let's fill these count maps with the data that you are analyzing there, that you gave in the path. Okay. And then let's plot it. Okay, it looks much better now. So, do you, yes. Yeah, shift enter, yes. Okay. Yes. Okay, do you have an idea on where the telescope was pointing here? Okay, this is the source, but we are not pointing to the source. Right, as I told you in the wobble part, the telescope is pointing here, and then here, okay, and then it comes back here, and then comes back here. We have forwards, okay. So the telescope is never pointing directly to the target, so that we can save time when we are going to estimate the background. Yes. Sorry? You. Yes, okay. So let's say that the first run, we have 4 runs here. Every run corresponds to 10 or 15 minutes of observations. Okay, it's defined on the fly by the user. The first run, the telescope was pointing here. It took, so we select this region as the on region, and the 3 red stars as the off regions. Then it observes here. When it comes back to here, it does the same, and now the orange points are the background regions, okay? They shifted a little bit, but it's not a problem. You made that question as well. Okay. Now we can very quickly estimate how the number of events grow over time, and how the significance of the observation grows over time. Something I forgot to tell you. We are using magic data here. So we have 2 telescopes, okay? This tool, the Gamma Pi, will be useful for CTA data. So everything you are doing here, you can repeat with CTA, okay? But you cannot do that now because we don't have CTA, okay? And okay, here you can see that the number of excess events, which are the events we are looking for, they grow over time. And here we can see that the background is growing as well, but just a little bit. And the significance, of course, grows, but it grows with the square root. It doesn't grows linearly with the counts. Here we can plot again just to highlight. This is the same plot as before, but just highlighting the source. We are changing the color scale. And this is something that I really want to show you. Oops. Okay. Here. So this is the counts map for the magic observations using 2 telescopes. I told you in the beginning of the lesson that we can do the same. We can do gamma ray astronomy with 1 telescope. However, the filtering of showers is much worse. Imagine if you have 2 telescopes, you can reconstruct the cascade much better. You can see the cascade from different angles, so you can tell better if it's a cosmic ray or a gamma ray. If you do with 1 telescope, this count map will look like this. Okay. In my screen you cannot see very well, but in your computers probably you can. You can see that in the middle there is some excess, but it's not that much. So this is the difference between monoscopic and stereoscopic observation. Stereoscopic, 2 or more telescopes. Okay, so we have a huge improvement in data quality with stereoscopic observations. And this is also for comparison. So you can see here that the background grows. Okay, the excess grows as well, but the background is always higher than the excess for one telescope. Okay, for 2 telescopes, we saw that it was the opposite. Okay, Gabriel. Oops. Oops, I'm sorry. This is a mistake. I did not realize that when I was doing it. The correct one is this one. It's the full number. It's 800, 1000, 1200. Okay. Okay, where are we? Here. Now we can fit the spectrum. You see here commented several spectral models. You can play with them if you want. But we are using the log parabola. So let's try to fit a log parabola to our data. Let's first check how is the histogram of energies. So this is the number of events as a function of energy. And finally, let's create our spectrum. Okay. Okay, this is the spectrum. Being honest with you, this is a quite weird spectrum, but I could not expect something much better if I modified the data by myself. Now, I modified it as I wished with a random component, so we have this. But this is right. If the data was real, this would be right. Okay. We can overplot the fit. You see a very particular thing here as well, which is a log parabola with a positive concavity. This can happen sometimes, but it's not that usual. Certainly not for the Crab Nebula that we are supposedly observing here. Okay, we can compare our result with the archival Crab Nebula spectrum. It's fine because I shake the data with my hands, but we are still close. And finally, we can estimate a light curve. For the light curve, I'm choosing to freeze the alpha and beta parameters of the log parabola. So I'm leaving free to vary only the normalization of the log parabola. And, okay. So this is the final result. Yes? Are you familiar with a log parabolic spectrum? We have 3 parameters in a log parabolic spectrum. The normalization, the alpha, which is the index, and the beta, which is the curvature. Okay. So we are freezing the shape of the log parabola and leaving only the normalization free to vary. Okay. So did you? Well, if you press enter, you arrive at here. And okay, this is the lesson. This is the part where I work alone. And now we arrive at the part that you can work by yourselves. I put some exercises here. You can choose one of them or 2 or 3 of them to do. And I can follow you talking directly to you. Okay, so you can change the number of beams in the LC, the light curve. Here, here the light curve is 1 per run, but here commented I leave away how to make beams. So here we have 3 beams for 4 runs. So of course you can play with these numbers in the way you want. This number here is in modified Julian day, okay? You can also redo the analysis selecting only one run, this in the flaring period, for instance, which may be interesting. And you can also change the spectral model. We use the log parabola model, but you can use the power law, the power law expansion cutoff. Okay. You can start. Feel free. If you have doubts, call me. Oh. Não, o cara respondeu certo. You're welcome. See you guys. Di mana? Ah. What?